So what we're going to be doing today, we're going to learn about a systematic way of like solving any circuit that we can possibly get. So far, what we know is that we know KVL and KCL. We know some sort of like connections that we can simplify down to circuit to some circuits that we know, basically voltage divider or current divider. And given that, we could just solve for whatever the question was asking. But what if we had some systematic way that we could follow, basically have a recipe that we could follow and solve for whatever the circuit is asking every time we're given a circuit without even thinking about like, okay, what node I should choose or like what loop I should choose? Well, in this lecture, we're going to learn about one of these methods. And the subsequent lectures, we're going to learn about like another method. Basically, there are two systematic ways of like solving any circuit. Well, not exactly any circuit. I'm going to talk about it. So they're called like nodal analysis or mesh analysis. So let's talk about them. So we have systematic ways to solve circuits. Well, the very first way is nodal analysis. And that's something that we're going to talk about today. Another method is mesh or loop analysis. And these methods are basically built on top of like KVL and KCL that we learned before. If you're looking at like nodal analysis, we're basically using KCL. And if we're looking at like mesh analysis, we're looking at like KVLs, but in a systematic way. And since KVL and KCL are linear equations, if I write basically the equations that are associated with them, basically if it's either like nodal analysis or mesh analysis, I'm going to end up getting a linear system of equations, right? So these two methods, both of them, these methods are both linear. And if we have like a linear method, what it means is that we have a bunch of like linear equations. And any set of like linear equations can be represented in terms of like matrices. So since these two methods are linear, what we're hoping is that like we got to be able to like write them in terms of like matrices. So these methods allow us to use matrices to obtain unknowns. How does it usually work? Like, how does like a set of like linear equations look like? Well, we can always say there is some matrix A. It's multiplied by the vector of unknown, and that produces like another vector. So this is a matrix or coefficient matrix. This is an unknown parameter vector. And this is like another vector, right? And if the number of unknowns is the same as the number of equations that we have, this A would be invertible. And if it's invertible, I can find X like simply, right? So I can find X to be A inverse times B, right? So the whole idea is that like if I have like these two methods, I got to be able to write it in terms of AX equals B. And then I can give it to my calculators, can find like A inverse, plug it in there, and find the unknown in the circuit, right? So the question is, how can we do this? Like I said, the very first method is nodal analysis. So let's see how it works. Any question about this? All right. So nodal analysis. Let's just assume we're given a circuit. Given a circuit. We follow the following steps. First, choose a reference node, which we also call it the ground. Right? But let's just clarify a few things in that sentence. What is a node? What is it? It's basically a portion of wire that connects a bunch of like elements, right? So whenever we're talking about a node, it's a portion of wire that connects elements, right? What is a reference node? What is a reference node? A reference node is a node in the circuit that we're measuring voltage across basically any other node with respect to that node. And we can choose any number for it. We can assign any number to that voltage node, which we call it like reference. What is the easiest number that we can assign to anything? It's 0. So we're going to choose like a node in the circuit, and we're going to set the voltage for that node to be 0, and we call that node a reference node, right? Can it be any node in the circuit? Absolutely. But we usually choose the one with the most connections to it. Because if we zero out that node, right, we basically got rid of like most connections and we don't really have to worry about it. So it makes it a little easier for us. So a reference node is any node in the circuit that we assume it has voltage of 0. Right? Again, that number can be anything. But for the sake of this course, on whatever courses you're taking from this point on, let's just assume it is 0 because it's easier. Right? The second step is to name all other nodes. So name all other nodes. There is an intermediate step here. I'm not going to give it like a new step name. And the reason for it is that because it's not applicable for every circuit. You can only apply it to like very special like circumstances. So I'm going to call it basically 2A. Another step is to simplify the circuit. If you see like some, parallel connection, series connection that is pretty obvious, you can basically like simplify it as long as you're not changing the configuration of your circuit, as long as you're not changing like the node's name. So simplify the circuit such that the node configuration does not change. Again, this step is not mandatory. And it's not applicable all the time either, right? But if you want, if there is a circuit that allows you to do that, you can always do that. Third step, write down KCL for all nodes but reference. Because we already know voltage at reference at 0. So we don't really have to like do anything about it. Last step, solve for unknowns. Right? Basically what it means is I'll like put them into like a matrix and try to like solve it. Right? Let's have a quick reminder about how we can actually write the KCl. We all know how to write it. I'm just going to give you like a quick reminder. Any question about like these steps? Are they clear? All right. So a quick reminder. Let's just say I have a resistance with value R. Let's call this voltage node here V1, this voltage node here V2. Let's just say current through this thing is I, and voltage across it is V. We know because of Ohm's law, V across a resistance is Ri. Right? We know that. But what is this V in terms of like these node voltages? What is it? It's just V1 minus V2, right? So V is V1 minus V2. If I plug this in here, I can compute I, right? So I here is V1 minus V2 divided by R. Right? If I told you like this is I prime, what is the relationship between I prime and I? The value is exactly the same, but the direction is opposite. How do we show that? Put a negative sign in front of it. So we know I prime is negative I, but I know I is this guy, right? So it's negative V1 minus V2 divided by R. I can distribute this sign over here, so I get V2 minus V1 over R. Right? Very simple. Now we know these two. We know node analysis. We know the recipe. Let's just do an example to see how we can actually apply it to like an example. Any question about this? We good? All right. Let's do an example. Let's just say I'm given this circuit. It's a bunch of like resistors. And a current source. Let's just call this I1. This is 0.5K. This is 0.5K. This is 1K. This is 0.5K. This is 0.5K. And this is I2. Now let's just say we know I1 and I2. Let's just say they're given to us. They're 5, 6. They're numbers, right? So we know it. So I1 and I2 are given. Well, let's just say we want to like solve for all the voltages, all the currents, and all those things. How do we do this? Well, let's go through our recipe. The first step is to choose a reference node. What do you recommend? Which node do you think I should choose? We usually choose the reference node to be the node with the most connections. So if I choose the one on the bottom, basically if I choose this guy, I have a lot of connections to it. Again, I could have chosen this one. I could have chosen this one. It's completely up to me. So I choose this one. Let's take a look at it. If I choose this one as my reference node, do you think this is different than this? Do you think this is a new node? No, this is exactly this node. Why? Because there's no potential difference there. How about this one? Is this one any different than this guy? Absolutely not. Again, there's a wire there. With the same logic, this is no different and this is no different. So the whole thing down here is exactly the same node, and it's my reference node, right? So this is a reference. Let's move on. Second step, name all other nodes. Well, do you think this is a node? This one up here. That is a node because it's a portion of the wire that connects elements. Let's just call it V1. How about this guy? Do you think this is a node? Of course it's a node, but is it different than this V1? Absolutely, because I have like this element in between. So that's V2. How about this guy? Is this different than V1 and V2? Yes, because there's like this element in between, so there is a voltage drop. So it's going to be V3. How about this guy? Is it a new node? No, it's exactly the same as V3. How about this guy? Again, it's not a new node. It's exactly the same as V1. Do I have any other node that I haven't accounted for? No, I basically took care of all of them. Step 2a, well, there's nothing I can do here, right? So I'm going to move on to step 3. I'm going to have to write KCL at every single node that I have but the reference. So let's start at writing a KCL at node 1. What does KCL tell me? It tells me whatever current that goes in should come out, right? So I'm going to assume a bunch of like directions. So I'm going to assume all the currents over here that are going out. Why? Because I wanted to. If you want it, you could assume all the currents are going in. Unless you're given the direction, you can assume whatever direction you want. For the sake of simplicity, I always assume everything's going out, right? You can assume everything's going in. You can assume some of them going in, some of them going out. As long as you make up your mind and decide on like something and stick to it, it does not matter like if you're choosing the current to go in or out. But as soon as you decide on it, you have to stick to it. You cannot just like say, oh yeah, I don't like this direction in the middle of your analysis. If you choose it, you got to stick to it, and you got to like solve the rest of the circuit using those directions. Like I said, what I like to do is that I'm going to assume everything's going out. So I assume like those things are going. So if I write a KCL at this node, what do I have? Whatever current that's going in should be the same as whatever current that's going out. Well, I1 is going in, right? Do I have anything else that's going in? Nope. It's the same as whatever current that's going out. What is this current? What is this current? It's V1 minus whatever voltage I have here, which is 0, divided by the value of the resistance. So that is V1 minus 0 divided by 0.5K. What is current here? What is it? It's a V1 minus V2 divided by 0.5, right? Minus V2 divided by 0.5. Well, this is like simple, right? I can just simplify it. I can write it as 0.5 I1 equals V1 plus V1 minus V2. Therefore, 4 times V1 minus 2 times V2 must be I1. This is my first equation, right? Remember, I1 is given to me. I1 is 5, 6, 7, whatever. I have to move on to the second node. So let's just write KCL at node 2. Again, I have to choose directions. Over here, this is already given. I already assigned a direction to it. I cannot change it. How about over here? Well, again, I'm going to assume they're going out, right? I have to write a KCL at node 2. What does it tell me? It tells me whatever current that goes in should come out. Is there anything that's going in? Yeah, this guy. This current is actually going in. What's the current? What is it? It's V1 minus V2 divided by half, right? Remember, this is how we compute current, right? Do I have anything else that's going in? No, everything else is going out. So that equals to, what is current here? It's V2 minus voltage at the ground, which we assumed it's 0. So it's V2 minus 0 divided by 1K. How about here? What is current here? It's V2 minus V3 divided by 0.5K. Right? Now I can take this term to other side. V2 minus 0, 1K plus V2 minus V3, 0.5 minus V1 minus V2, 0.5K, and that's 0. I can simplify it, and what I'm going to get is minus 2 times V1 plus 5 times V2 minus 2 times V3. That should be 0. Right? If you look at this, I still have 2 equations but 3 unknowns. I need one more equation to be able to solve this basically system of equations. But I can do this because I have the node 3, right? So I'm going to write the KCL for node 3. So KCL at node 3. Let's see what we have. Again, this direction is given to me. This direction is given to me. I can assign a direction here. I'm going to assume it's going out. Right? So what's the KCL at node 3? Whatever going in should be the same as whatever's coming out. So I have this current going in. What is the current? It's V2 minus V3 divided by 0.5K. I have I2 coming in, right? I don't have anything else that's coming in, so I have this equals this current that's going out, which is V3 minus 0 divided by 0.5K. Right? Well, I can simplify this, and what I'm going to get is minus 2 times V2 plus 4 times V3. That equals I2. Now what I have is I have 3 equations, 3 unknowns. I can put it in a matrix. How do I do this? Well, I'm going to start by writing down my unknowns. So it's V1, V2, V3. There should be a matrix, which is a coefficient matrix. If I multiply it by my unknown, I should be getting another vector. Right? Let's look at this equation. What does this equation tell me? It tells me I have 4 times V1 minus 2 times V2 plus 0 times I3. That should be I1. So I have 4 times V1 minus 2 times V2, 0 times V3. That should be I1. Right? Basically, I grab all the coefficients and put it in the row of this matrix. How about the second equation? That's basically minus 2 times V1, 5 times V2, and minus 2 times V3, and that should be 0. Again, let's check it together. I have this thing that should be multiplied by this guy, so I have minus 2 V1, 5 V2, minus 2 V3. That should be 0. And the last equation I got is this guy, which is 0 times V1 minus 2 times V2 plus 4 times V3. That should be I2. So it's 0 minus 2, 4, and that should be I2. Right? Now I wrote this guy in terms of some known matrix X, some unknown vector X, and some vector B, which which is unknown, right? If I want to find x, x is A inverse times B, right? Any question on this? Is that clear what we did? Yes? Let's quickly look at this guy. What are we doing? So in nodal analysis, we start an analysis by writing KCLs. And if you guys remember, KCL is a rule for the currents, right? It says like the algebraic sum of all currents should be 0. But look what we found when we actually solved our KCLs. We found node voltages. That's a very important point. Whenever we're doing node analysis, even though we're writing KCLs, but what we're solving for is node voltages. We're going to learn when we're doing like mesh analysis, which as you can guess, we're going to write KVLs, right? So even though we're writing KVLs, what we're going to solve for is just going to be currents, which is the dual of this guy. So let me just like make that point quickly. Remark. Doing nodal analysis, we always solve for node voltages. And if I know node voltages, I know everything else in the circuit, right? For example, if I ask you, what is voltage across this guy? Since I know V2 and V3, I know voltage across this is like V2 minus V3. If I ask you what current through this guy is, you know exactly what it is. Because you know voltage across it, you know the value of the resistance, you can compute current. So as soon as you compute node voltages, you can compute anything else in the circuit. Okay? Another point I want to make is that nodal analysis is the most comprehensive way of solving a circuit, meaning you can apply it to any circuit that you're given. We cannot say the same thing about mesh analysis. This method holds for any circuit, whether it's planar or non-planar. Basically, if I can plot it on a piece of paper or not, I can apply this method to it. We cannot do the same thing for mesh analysis. We're going to get to it. So keep that in mind. This is very general and can be applied to any circuit. Any question before I move on to like another example? Very good? So let me do another example. Example. Let's just say I'm given this guy, 6 milliamps, 2K, another 2K, and another 2K. And let's just say I have another current source here with value 4 milliamps. Okay? Let's just solve for everything in this circuit using nodal analysis. What is the first step? Well, we know the first step is to choose a reference node, right? What do you guys suggest? What should I pick? The bottom node, right? Because it has like the most connections to it. Again, it's completely up to me. If I want to choose this one up here, I can, right? So let me just choose like this one down here. What I'm claiming is that this node is exactly the same as this node, is exactly the same as this node, and it's exactly the same as this node. Right? There is no potential difference. All of them are the same. And since I called that my ground, my reference, I know the value for it should be 0. So I know voltage at that node is 0. So this is my reference. Right? What is the next step? Name all other nodes. Well, let's determine what nodes are. I'm claiming this is a node. I'm going to call it V1. Is that a node? Obviously, it's a node, and it's completely different than this ground. How about this guy? Is this a new node? Or is it the same as V1? That's a new node, right? Because there is a voltage drop across this guy, so this is going to be a new node. How about this guy? Is this a new node? No, this is exactly V2. How about this guy? Again, this is no different than this V1. Do I have any other node? No. I basically took care of all nodes. There is no other node left here. Right? 2A, again, it's optional, tells me I can simplify the circuit. Well, I can, right? If I look at these two, they're in parallel. I can combine them into one without actually changing my node names, right? Again, it's completely optional. I'm going to do it, but you don't really have to do it, right? If you're given this circuit, you can keep it the way it is. I'm going to simplify it. So if I simplify it, my circuit would look like this. I have this 3K. I have this 6 milliamps. I have this 2K. I have this 4 milliamps. I have 2K and 2K in parallel. I'm going to replace it by a 1K resistance, right? The rest remains the same. This guy down here is still my ground. This is still V1, and this is still V2, right? What is the third step? Write down KCL, right? I'm going to have to write down KCL for every single node but the ground. Well, let's do it. KCL at node 1. Again, I'm going to assign some current to it, whatever I want. Again, I'm going to assume everything is going, right? KCL tells me whatever current that goes in should be coming out. What do I have? Do I have anything that's going in? No, so 0, right? What is this current? What is this guy? That's this voltage minus this guy divided by 3, because V1 is voltage across this, right? So I have V1 minus 0 divided by 3K. How about this guy? What do I have? It's V1 minus V2 divided by 2K. And I have this 6 milliamps, right? I can simplify it. The common denominator is 6. I can simplify it. And what I'm going to get is 5 times V1 minus 3 times V2. That should be minus 36. Right? It's just a simplification. It's not a big deal, right? Just look at the common denominator. It's 6. So that would be 2 times V1 plus 3 times V1 minus 3 times V2. Take this one this side, multiply it by 6, and that's what you get. Right? How about a KCL at node 2? I already know this direction, so I cannot change it. But I can assign a direction to this guy. Again, I'm assuming it's coming out. What do we have? A KCl. It means coming out should be the same as going in. What is it that's going in here? I have V1 minus V2 divided by 2K, right? Do I have anything else that's going in? No. Equals whatever that's coming out. I have this current. What's the value of this current? It's voltage across it divided by the value of the resistance, right? What is voltage across it? It's V2 minus 0 divided by 1K plus 4 milliamps, right? I can take them all to like one side. Basically take this guy over here, take this guy over there, and simplify it. What you're going to end up getting is minus V1 plus 3 times V2 equals minus 8. Right? Again, that's just a simplification. It's not really a big deal. Now I have two equations, two unknown. I know there is a unique answer for this set of equation. Let me put it in a matrix. Again, I have my unknown vector. I should have my coefficient matrix multiplied by this unknown and give me some constant. If I want to present the first equation here, I have to like put the coefficients on the row for this guy. So I have 5 times V1 minus 3 times V2. That should be minus 36, right? The second equation is minus V1, so it's minus 1, plus 3 V2. That should be minus 8, right? Again, this is A, this is X, and this is B. I can compute X, which is V1, V2, as A inverse times B, right? If I do that, it turns out V1 is minus 11 volts. V2 is minus 19 divided by 3 volts, right? Now we know these things. Let's answer a few questions. Okay? Question 1. What is voltage across 6 milliamps current source? Basically, what is voltage across this guy? What is it? What is voltage across this? It's V1 minus 0, right? Because we already computed that. So the answer is V1 minus 0, which is minus 11 volts, right? Question 2. Let's call this guy over here R. Okay? So this 2K, we called it R. The question is, what is voltage across R? What is it? What is it? It's V2 minus 0, right? So it is V2 minus 0, which is minus 19 over 3 volts, right? What is current through it? Question 3. What is current through R? What is it? Well, I know voltage across it. I know the value of the resistance. I can compute current through it, right? So I know I of R is V across R divided by R, which we know it's V2 divided by R. It's minus 19 divided by 3 divided by 2K, which is minus 19 over 6 milliamps. Right? Let's call this guy over here R prime. Okay? What is voltage across R prime? Question 4. What is voltage across R prime? What is it? It's V1 minus V2, right? It's V1 minus V2, which is minus 11 minus 19 over 3. This is going to be minus 33 over 33 minus 19, which is plus 19 over 3, which is 14 over 3 with negative. Right? There's a negative sign here. Right? What is current through it? What is current through R prime? What is it? What is it? I know voltage across it, so I can find current through it. So let's just call it I of R prime. We know it's V R prime divided by R prime. V R prime is this minus this, so it's V1 minus V2 divided by R prime, which is minus 14 over 3 divided by 2K, which is minus 14 over 6 milliamps. Right? So as soon as I know node voltages, I know everything in this circuit. I can compute whatever the question is asking. Right? Any question? Any question? Is everything clear to everybody? Remember, let's just have like a quick review. There are two systematic ways to solve any circuit: nodal analysis, mesh analysis. Nodal analysis utilizes KCL and basically writes KCL for every single node that we have. And what it basically produces is node voltages, even though we're writing KCLs. Right? What we're going to be doing next lecture, we're going to do a few more examples to just see how we can apply this method to any circuit, and what are the obstacles that we might run into, and how we can get around it. And then afterwards, we're going to talk about like mesh analysis, which is exactly the same as this, but rather than solving for node voltages, we're going to solve for like loop currents. But essentially, it is the same thing. However, as I mentioned, this is a more general way to solve any circuit. Right? Any question? Yes. A is the coefficients. Is the coefficients. Yes. There is no real meaning to it because you're simplifying the circuit, right? So it's just a coefficient, right? If it's a very simple circuit, yes, you're right. It's the inverse of like resistors. But since there is much more to it than like having like a simple like series or like parallel, so it would be a combination of like those things. So it's better to just like think of it as just coefficients that are basically representing like the coefficient like a specific like voltage. Any question? We're good? We understood what's happening? Now we understood what's happening, please take a piece of paper out.